Hello everyone, my name is Randall Fowler and I'm going to be continuing our LTspice workshop and I'll be covering Netlists. So first you might be wondering why am I using Zoom over OBS. When I was using OBS it kind of consumed my computer, it overwhelmed it, and Zoom seems to be recording just fine, so I'm going to work with this. So to get started, I have this slide here that just kind of shows a little generic facts that we can remember when we create our net lists. Basically, LTspice, it's not case sensitive. You can use uppercase, lowercase, doesn't matter at all. You can switch it around to declare something uppercase and use it as lowercase. One of your nodes, and if you don't understand this at first, you will at the end, but one of your nodes has to be declared as node 0 because this is our reference node. You could consider it ground or whatever you need to think of it as. So then another thing is, you might not understand this right now, but the first line of the net list is always reserved for comments, and I will show that in every net list I create. Another thing is we have reserved letters such as V, I, R, L, C, and X. V, independent voltage source, I, independent current source, resistor, inductor, capacitor, and subcircuits. And subcircuits, that could be anything, but typically we use a lot of op-amps as subcircuits, or you could create whatever subcircuit you want as a netlist and you can reuse it. Okay, so moving on, you don't need to use units in LTspice. You don't need to declare it as volts. You don't need to declare it as farads or ohms or any units for any of our components. We do have prefixes though. You could use the letter P for picofarads, if you're using a capacitor. You can use any of these. I believe there are more, there should be. But these are just kind of the general ones that you probably will be using more often. All right, so some of the basic syntax, and I will obviously be going into this even more when I actually open up these projects. But basically when we type in, here, to get started, let me go ahead and open up a notepad. And if you want to read this, it says most of the components, let me make this a little smaller. There we go. There we go. Okay. So if you read this, it'll say most of the components will follow the same syntax. So we want to use, an independent voltage source. What we can do is we can say, okay, V, which is, reserved for independent voltage sources. And then we have to have a name right after it. So in this case, you call it V1, or you can call it VN, or you can call it V whatever. Doesn't matter. So I'll call it VN. And then right here it says N plus and N minus. Those are your nodes. So these are for polarities. If you notice that every single one of these follow the exact same syntax, where the positive node will always be first and the negative node will always be second. If you use a sub-circuit, it could use many nodes as your inputs, but let's just start with this. So basically, if we're starting out a circuit, which I'll show in a second, you might want to use a reference, and I like using 1 and 0 to get started, because 1 is the first node, and that's where I usually start with an independent voltage source in our circuit. And then a value, you could say 5 volts, or you could just say 5. Both are the same. If you want 5 millivolts, you could do 5M for milli. If you want gigavolts, which I don't think you'd ever be using, you can use a G. Megavolts. And you can go over these slides if you need to reference them, or you can even just type in and Google it. Prefixes for LTspice. All right, so, and here's some other ones you might want to know as well. So if you use square waves or sinusoidal waves, then these are the syntax for using those. And then if you want to do a frequency domain response, so if you're doing like a Bode plot or something, this is helpful, just because instead, right before you put the value, you can type in AC, and then you can put the magnitude of the alternating current. And I believe you don't need to put the phase angle. It'll assume that if you don't put a phase angle, it'll assume it is 0. But if you want to like do a phase angle or phase shift, you can. All right. So let me have to pull up that. So I went ahead and I did already finish all these, but you can go ahead and ignore this, or you can reference it right now if you want to. Basically, I'm going to be going over 4 different circuits and doing all of them in LTspice for you guys right now. First thing I'm going to do is I'm going to do a DC adapter. Well, let's go do a DC adapter. First thing you need to do is open up LTspice. And I like to have, you know, our actual circuit picture right next to it when I'm starting these. So how do you get started? Well, for schematic, you go up here and click, but that's not what we're doing. We're doing a netlist. So in this case, you probably should open up a notepad like I did. But here's the first issue is first line's reserved for comments. So we need to skip down 1 line. This line is for comments. I can go ahead, file, save as. I already have a little thing. I don't want it as a text file. I want it as a .cir file. So I could call it LTspice workshop example 1.cir. I already have the file. I'm just going to save over it because I'm just going to make it good again. All right. So this is our netlist. I can actually close it. Go up here to open file. And ooh, that's not the right file. There we go. All these. Let's click this one. This is the one I just saved. I'm going to change this. I like to use the top line as our label. So we could do LTspice workshop example 1. Make it symmetrical. But you could, to make comments, because the first line is reserved for comments, you can't actually start your netlist in the first line. But you can create comments after that anywhere you want. So I'm going to say, this is our DC adapter. You don't need that second one. I'm just doing it for, you know, symmetry. Okay, well, let's look at this. We already are started, actually. We have a VN. VN is this guy right here, our independent voltage source. I used 1 and 0, which means that basically I said, okay, the negative terminal here is going to be 0. See, it's blue. It's going to be 0. And then right here is going to be 1, because that's a node right there, and that's going to be node 1. This is a node right here, node 0. That's how I get started with a netlist, is I take a look at our circuit, I reference all of our nodes, and I name them. So I already named 0, 1, and there's only one more node right here, this big one right here. So that's another node. You don't need to name them numbers. You can use words, so I'll use out. So I have this voltage source, and then I have a diode. Let's create a diode. So let's say D1, and it's the positive lead of a diode is going to be that side, and that side's the negative. When it comes to capacitors and resistors, it really doesn't matter, you know, for direction. It's not going to really change anything. However, when you analyze the circuit, it will change the polarity of, you know, your voltage drop or your current. So I'm going to treat this as that direction, where this is our positive to our resistor, even though it doesn't really matter. It just matters when you're measuring in the polarities with this block. Okay, so diode 1 is going to be the positive, and then out is the negative. And we don't actually have a value for this diode, but you will be putting something else, and I'll go back to that. So now the next thing is we need a capacitor, C1, and we're going to go from out to 0, because that's what it does. It goes from this node to that node. And then our capacitor, let's just say, I don't know, like what, 0.01 microfarads. I'm making that up. And then R1 we're gonna go from out to 0 because it's gonna be parallel with the other capacitor. And then let's say this, what, 10K? All right, that's our whole circuit. We have our voltage source, a diode. The voltage source goes from 0 to 1, negative and positive, those terminals. Our diode goes from 1 to out, from positive to negative. And when you do current sources, if this was a current source and it was to go, it would be going in that direction, or no, it'd be going in that direction. Then this side would be the positive and that would be the negative, because you have to think about it in terms of which way the current, oh no, actually I'm wrong. Oh gosh, why am I mixing those up? You need to go in the direction that the current's flowing, because current's gonna be flowing this way, current's gonna be flowing that way. Since this is 5 volts and we're considering this as 0, basically, since current is flowing in that direction, you need to realize that's gonna be a positive and that's gonna be our negative. So when you declare, if we did a current source, all we'd have to do is just that, or not, that's IN, and it would be the same thing. Okay. Ooh, let's not do that. Okay, so we have all our components. Next thing we need to do is, this diode is actually not a component that we have. We do not have that in our library here. So what we do instead is we need a component. So what you can do is you can go online, and if you're looking at diodes to purchase, then you can actually look up those diodes and pull up that netlist off of you know, the Spice website that they use. I believe it's Analog Devices, right? So this diode we're using, I took the netlist for that diode online, or you can create your own subcircuit. If you look at my folder, right here is actually a diode that I brought in. This diode 1N4148. And if you want to use it, all you have to do is type in .include, and then you just do the file name, 1N4148.cir. That includes the diode now. We don't even need to worry about it. Okay, next thing we need to do is we need to use our operators. So .op, which is going to do the operation, and .end, which symbolizes the end of the netlist. I'm going to run it. Oh, got our value. So this diode, we already created a diode, but we need to reference this circuit, or this diode specifically. So instead of a value, you need to put down the name of the diode. And it might vary, and I'll show you that in a moment. So now let's run it. Perfect. So let's look at our circuit. So we have 5 volts here. Our output voltage here is going to be 4.45 about. And the reason why it's 4.45 is because the diode is acting basically like a voltage supply, where it is dropping our voltage from 5 volts. It's dropping it by about 0.55 volts. And so because it does that, this is about 4.45. And then that is it's going to be doing a complete drop of that voltage. So for the current here, we would have 4.45 volts divided by 10 kilo ohms. That seems about right to me. And that's what it's saying. It's giving us the current through the diode, the current through the resistor. It shows a current through the capacitor here, but if you notice 10 to the negative 20th, that is basically 0. All right, so I'm gonna go into a little bit more detail on this. This file right here, let me go ahead and open it up. I like to sneak a peek into our files, our circuits that we have. So I'm gonna open it. Here it is right here. That's not a lot going on. It might look kind of confusing because you have all this, but right here you have a dot model. So it's creating some kind of component, which I believe one of our members will be going into another video on just how to do subcircuits, or how to find them. But basically, this is the name right here. We have a dot model 1N4148. In this, we do in dot include the file name. And then right here, we use 1N4148 because that is the name dot model right there. If I change that to diode, like DIOD, diode, I don't know if that's reserved, but then right here, I just have to put in diode. So another thing, which I'm not going to save that. Another thing though, is that actually one of my classes, a professor just gave me this. He didn't give me the file. He just gave me this bit of code, the dot, this whole thing. Well, what you can do is you can just paste it in there and now you can use it. I don't include the file name anymore, but if I run it, it still works. So if they give you this and you don't like this bulky thing in your, your net list, you can open up, a notepad. You can open up a notepad. You can just take it, copy it, paste it there. Oh, first line's reserved for comments. You can reference, you can say 1N4148 is a diode. And you could even put down the syntax like D name, N plus, N minus, and then you could put down, you have to put in 1N4148 for the syntax. And then all you have to do is do a dot save as, and save it as a dot .cir file again. Now I already have this, but you just save it as a one and the name of the file. You don't necessarily have to name it that, but you do have to know the file name for when you include it. Because, don't save, because right here, if I'm going to use it, because I saved that file already right here, I just do dot include 1N4148.cir. Okay, so the next thing I'm going to do is I'm going to take a look at this and I'm going to think, ooh, this isn't actually what the, putting in like a 5-volt, DC voltage source right here, that's not a good idea. Like this is supposed to be a DC adapter, which means that we're putting in an alternating current and we should be getting out a direct current. So how do we do that? This VN right here, this is just 5 volts constant. We can actually change that. We could do sine. I don't think you necessarily need parentheses, but I use them. So the first number is going to be our offset, which is going to do is 0. So that would be 0 volts. So that's our DC offset. So if you want it oscillating at like 5 volts from like 6 to 4, then you'd put in, if it's oscillating from 6 to 4, you'd have a DC offset of 5. Let's do an amplitude of 4.7 volts. You don't need the V, but I put it there. And then this is going to be our frequency, which I'm going to say is 20 kilohertz. This is great. Let's try to run it. Oh, that's not what I want. That's not good, right? That's because we need a different operator here. You could actually get rid of this guy if you want. I like leaving it. It doesn't really do anything. But next thing I'm going to do is I'm going to do a dot tran. So what that's going to do is that's actually going to run time for us. It's going to actually graph everything. So the first number when we do a dot tran is going to be our time increments. So in this case, I'm going to do, let's do every 50 nanoseconds. I don't need the S. And let's run it for 100 microseconds. Why am I doing it like that? Well, it just gives it a few periods to run and it'll show. Let's run it. Ooh, I don't need this. No, don't save. That graph, I want this to be bigger. You can manually open it up or you can just fully expand the screen. Close that and let's just run it again. it'll auto adjust for us. Okay, so now what's going on? This is our graph, there's nothing in it. We have to add our signals. So I right click onto the graph, I hit add traces, and if you noticed, we only have 3 nodes. We have a reference node, which isn't going to be coming up because that's going to be our reference. And then we have 2 other nodes. We have an input. I'll go ahead and put the input in there. And then we have an output. If you misclick, like I just misclicked V1, so now it says V1, V out, V1, you can just backspace. Or if you click V1 and now you have it in there and you hit OK, well, you can go over here and you can click delete trace, and now it's just the 3. Whoa, now we have something. This is gross. I don't like, I like the green. The green's pretty, but the blue, when you turn in assignments, or if you're doing this to show people or documenting it, blue is really hard to see. If you right click onto the traces, like right here, if you right click, you can change the colors. I like pink. Pink's really easy to see. You can also change the expression. When I say change the expression, I mean you can like, you could do -2. It should bring it down. You could do -V1. So now what it'll do is it'll take our signal and it will subtract V1 from it. We don't want to do that. I'll show you, but yeah, that's not actually what we're analyzing though. It can be helpful for some applications. So let's hit OK. This is what we're looking at. We have green as our input, pink is our output. So that's not bad. We're having a alternating current come in, and our output, it's kind of constant. It's not that great, but it's okay. Well, let's play around with this. So I already know how this works, but basically the capacitor value is gonna be influencing this line. So how do we change this? How do we make it a little bit better? Well, so what I'm gonna do is I'm gonna do a dot step, and that'll give us a variable for one of our components to like change around with. I'm gonna name the variable, or well, we have to do step param for a parameter, and then I'm gonna name the variable y. You can name it x, you can name it variable, you can name it, I'm gonna name it y. Y is an easy one. Now, I believe what you can do is you can actually write down increments. You could do in increments of 0.01 micro, and then you can start it from 0 to, or you could do 0 to like 1 farad, or that's really big, 1 microfarad. So that you could do it like that, where you have a step size, start, stop, or because that'll give you a bunch of stuff and it'll go through a whole range. Or you can type in list, and now y will be equal to exactly what you give it. So I'm gonna say 0. Or let's say 0. Let's say 0.001 micro. Let's say 0.01 micro, 0.1 micro, and 1 micro, and then sure, 10 micro. So that's going to be, y is going to be equal to each one of these. If I run it, it's not going to do anything because we have to say, what is y? Well, you take this value we have here and you replace it. That's not right. You have to replace it with curly brackets and the y. So you have your variable here and then you have curly brackets. So now let's run it. Whoa, a lot more going on there. So this might be kind of hard to analyze, but you can see some changes. The capacitor definitely influences what's going on. So let's go ahead. I kind of got a good idea that the capacitor is the main source of our changes. Because if you didn't know, let's go ahead and put it back 0.01 micro. Let's say we wanted to do that for watt or the resistor, change up the resistor, then you could do, 1K, 2K, 10K, 20K, whatever, run it. That did something. but it helps you to kind of see the graph and what it's going to be doing, listing off different variables. If you have a lot more, it usually changes colors. I'm not sure why it isn't changing more colors, but you know what you can do though? Here, let's go do the other one again. And then, okay, so let's run this. Now, how do we check the differences between all these? Ooh, I can click on the graph. So I just clicked on the window. Ooh, that's bigger than I want it to be, but that's fine. Ooh, can I do that? Yeah, perfect. Okay, so click on the window and right click. Oh, wait, no. Click on the window and then you can go up to File and then you can do an export data as text. Okay, so one thing I want to make notice is if you're typing and you're like, you know, making your net list and then you go up to File, you don't see it. It's because you have to be clicking onto the window with the table or with the graph. Then you'll see the export as data. So now I click export as data. If you notice, it says V1, V out. Those are the two variables that we will be getting. And I'm going to hit OK. The reason why you might want to do that is if you want to bring it to Excel. Let me go ahead and open up. Here it is. It just saves it as a .text file. I'm going to go ahead and open it up. Ooh, wow, there's a lot going on in there. Huh. So now what you can do is you can see, okay, first variable here is time. Every single one of these is time. And then second variable is VN, or is V1, which is our input. Everyone's right here. Our output, everyone's right here. And then right here it says step information y equals 0. And it says run 1 out of 6. That means because we did 6 different variables. We had 1, 2, 3, 4, 5, 6. And if you notice, if I scroll down, I might have skipped it. There should be one right around. I'm being impatient. It's right around right there. Well, that's 4 out of 6, but there's several throughout this whole thing. If you notice, it'll go through and it'll do every single one of these. This is for 100N. Whoa. Oh, the reason it says 100N is because 100N is also equivalent to 0.0 or 0.1 micro. So this guy right here. Because this would be 10N, this would be 1N. Okay. The reason why you might want this is if you want to put it in Excel, because now what you can do is you can go to the top, you can just literally copy all of it and throw it in Excel, and then you can split up your information. And this is a lot faster to export and just analyze it in Excel spreadsheets. Okay. That's useful information, I'd say. But I think I'm pretty much done here. I can get rid of this. I don't need the variable thing. But if you want to play around with it manually, you could say, okay, 0.01. That was our original. So let's run it. That's what it looked like. Okay, well, what happens if we make the capacitor just gone, basically? That, all it's doing is basically just picking up the diode and the resistor. The capacitor is basically gone. Okay, so what if we do 0.1 microfarads? Ooh, that looks pretty good. So our alternating current as the output, it's pretty constant. You know, you have a little divot there, but you can play around with the value. What if we make it 1 microfarad? Pretty straight, pretty flat. They make better circuits for DC adapters, but this is like the most basic DC adapter you can create. All right, well, I'm done with this example.